Hello everyone, and welcome to the Geometric Computing with Python course that is being presented at SGP 2021. The presenters of the course will be Zongshe and me, Daniele. And before we start, I would like to thank all the contributors to the open source library that we're going to use in this course, that are libigl, meshplot, and polyfem. This course will not have been possible without all their efforts. The course will be presented by Zongshe. He's a PhD student in my group at New York University. He's gonna graduate soon and he's currently on the job market. I am Daniele. I'm an assistant professor at NYU, working on geometry processing and scientific computing. The goal of this course is to learn how to design, program, and analyze algorithms for geometric computing. And in particular, this course is going to give you a hands-on experience with problems related to shape modeling, geometry processing, and simulation. After this course, you're going to be able to code, first of all, I understand and code many algorithms in geometry processing, and you're going to have all the tools that are needed to do research in this direction. And you're going to learn a bunch of libraries that allow you to automate and be more efficient in how you spend your time by automating and taking care of many of the basic things that are useful in geometry computing research. Before we delve into the more practical part, I would like to spend a few words about what is geometric computing. It's a discipline that is at the intersection between discrete differential geometry, which is used to describe and represent surfaces and volumes and properties and operators defined on them, numerical methods for solving partial differential equations. Usually the focus is more on the quick and approximate solution of them, and especially in the work on solving these PDEs on irregular domains that can be either designed from scratch or acquired, for example, with a 3D scanner. There is also part of high-performance computing to make this algorithm usable on real-world data. So there is also a part on like how to accelerate computation using either vectorized computation or distributed computation or GPUs. And finally, there is also a part of human-computer interactions, because at the end of the day, people are using these tools and they need to be usable. So geometric computing is somewhere at the intersection of all these four disciplines. And one of the things that is happening now, that the amount of data that is used, especially by data-driven method, is growing. It's also interesting that geometric computing is the tool that can be used to work with large collections of 3D data. Like, we are the experts in tools and algorithms that can process and prepare large collections of 3D data for further analysis or use. I just would like to go through many of the common steps in a geometric computing pipeline. I mean, usually you don't consider all of them at once, but let's say that we start from a physical object, and one important task is converting into a usable model. So by using a 3D scanner, you can convert it into a collection of range images. Every range image is just an image where every pixel does not have a color, but has a depth instead. When you have multiple range images, you can combine them into a single model. This model, usually it's initially unstructured, made of triangles, and then depending on the application, you might want to convert it to a more structured representation made of quads, for example. And after this is done, this kind of models can be used in many applications, including animation, physical simulation, fabrication, visual effects, and structural analysis, for example. But there are many more. Let's take one of them. Let's say that we want to use this geometry for fabrication. Then the questions are, how can I prepare this geometry to be sent to a 3D printer? And then, like, after you produce the object, is the object going to be stable, robust, realizable by that printer, and so on. So all these problems in here, you see that they have one common denominator, which is they're working with 3D geometry. And so the tools and the algorithms and the problems you're going to be faced with in this course all involve working with 3D geometry, and we're going to see basic building blocks that are useful for many of the arrows that are in this slide. So the course is going to be divided into 3 parts. There is this introduction that I'm giving right now, and then Zhongxie is going to give a hands-on introduction to using Python for problems in geometry processing and visualization, and then in a second part on simulation, and then we're going to wrap it up with a live Q&A. So I encourage everyone that is attending this course to follow the explanation and ideally already play with the setup that we're going to use. To get started with this library is actually quite straightforward. If you are on Windows, Mac, or Linux, as long as you have Conda installed, these 5 lines is everything that you need, and after these lines are executed, you're going to have all the library installed and ready to use on your machine. Very quick overview of the main libraries that we're going to look at. And just as a side note, these libraries are cross-platform, so they will work both on Windows, Mac OS, or on Linux. So the first one is Meshplot, which is a library for visualizing 3D geometry. It allows you to very easily pass a collection of vertices and faces. I'm going to describe in more details later what is the format, and allows you to directly visualize the mesh inside a Jupyter notebook that will make your life much easier because you can just see immediately the result of a computation. The core part of this course is going to be on libigl. This is a collection of many algorithms for geometry processing that has been recently exposed to Python. So we're going to use this library through Python, even if originally this is a C++ library that you can, of course, use from C++ too. And finally, there is Polyfem. This is a finite element methods library that allows you to solve PDEs on 2D and 3D geometries. And we're going to see in this course how to use it for computing an elastic deformation. One thing that binds together all these libraries, in addition to the fact that they all work with 3D geometry, is that they use the same data structures, or actually they don't use data structures. And I'm going to comment more on why this is the case, but first let's take a look at what I mean by they don't use data structures. So the main object that we're going to deal with is a triangle mesh, which is a collection of points and triangles. The way we are going to store this mesh is by representing every vertex with a set of coordinates. Every vertex in space is going to have its own x, y, and z coordinates. And every vertex will have a triplet. And what we're going to do is take all these triplets and stack them all together into a single matrix that has 1 row for every vertex and 3 columns, 1 for x, 1 for y, and 1 for the z coordinate. So the entire representation of a geometry of a mesh is going to be a single matrix. Then the question is, how do we encode the triangles? And now one way of doing it is to take every triangle, consider the orientation of a triangle, this is important, and simply represent the triangle by using the 3 indices of vertices. The orientation is usually picked in such a way that if you move clockwise, your finger is going to point to the outside of a mesh. So in this case, in this representation of the orientation matters because it's going to be depending on the orientation that you pick, the eventual normal of your surface will point on one side or the other. So after we have this representation of one single triangle, we can do the same that we did before. So now we're going to have many different triangles. We take them all, everyone is a triplet of indices, and we stack them together into another matrix. Now this matrix has 1 row for every triangle and 3 columns because we have 3 indices for every triangle. So now this matrix V that we saw before for the vertices and this matrix F is everything that we need to encode this mesh. So the same idea is going to be used for other things, like for storing connectivity between triangles. We are also going to use matrices and so on. So our what we're going to do for all these libraries is to try to use only row matrices. So this is probably strange. Like, why would you stick with such a simple representation instead of like taking advantage of, for example, more object-oriented constructions that allows you to be more careful and have type checking and so on. Well, the big advantage of working with raw matrices is that they are, first of all, very efficient in terms of memory and cache, so they tend to lead to algorithms that are faster, but they also have another major advantage, which is that they are trivial to copy and to serialize. And what this means is that since we only use raw matrices, it's going to be very easy to exchange data, for example, with NumPy, or with PyTorch, or with TensorFlow, or MATLAB, or OpenCV. And so by using this simple format, it becomes suddenly very easy, especially if you work in Python, to exchange data with other libraries that you might use. And so to combine features of different libraries without having to do complex conversions between different types. One more thing that is specific to the mesh representation that we use is that we never use pointers, but we only use indices. And this is something that will make your life much easier if you'll have to debug this thing, because you can print them, you can look at them, and it's much easier to not get memory corruption if you use indices instead of pointers. But the big advantage is really, as you will see later, that it's possible to exchange very easily data between different libraries. So this concludes my introduction, and Zongxi is gonna take the microphone now and start with a hands-on introduction to geometric computing with Python. Thank you very much for being here, and I hope you're gonna enjoy this course, and I encourage you to prepare questions for the Q&A sections that will be at the end of this course. Thank you very much.